Okay, today we are going to talk about a few topics. The first is actually related to the project. So in the project, we are going to implement um, a approximate nearest neighbor search algorithm based on product quantization. So essentially, there are two papers, but we summarize most of the important things here. But for more details, you can always refer to the paper. Although the notation-wise, there could be some small differences. Okay, so the problem we are going to deal with is the nearest neighbor search and its variant. So this is actually a very fundamental operation in database and in machine learning and also in multimedia retrieval, etc. Um, and also in terms of the computational theory, this is also very important. Um, so the problem is actually best easily described in a low dimensional space. Sorry, but it generalized to multi-dimensional space and with a kind of distance functions as well. So so let's assume that it's a two-dimensional space just like this, and we have a query queue, okay, and query queue. So we have a query queue, and what we need to do is to say, and all, there are a bunch of other objects, let's say x, a, b, or let's say three data points. So there are two-dimensional points, and we can measure the distance between, any two objects, let's say q and x, right? Um, and by default, we use Euclidean distance. And one of the things we want to do is to find the nearest neighbor. So within this data set, if you compute the distance, and you can see that A is the nearest neighbor. And it turns out that there are several variations. Um, so one of the variations is they all try to relax a few things. One of the things is actually you can say, okay, I don't really um, insist on getting the real nearest neighbor, but I'm okay as long as the returned points are not too far away from you know um, the nearest objects. So one of the notion here is actually called 1 plus epsilon approximate nearest neighbor. So this actually means you return any objects such that the distance uh, to the query is at most 1 plus epsilon of the nearest neighbor distance. So in this picture here, the nearest neighbor distance is actually this one from Q to A. And as we can see, basically Qx, this vector, is actually smaller than 1 plus epsilon of this QA vector. Okay, so that's why x actually can be returned instead of a as it's 1 plus epsilon nearest neighbor. Um, Another extension that instead of returning only one point, I can return more than one point. So if I return k point, this is the kn version of the problem. So the problem is actually very fundamental for us to understand what kind of things we can do. Um, so in low dimensional space, usually the problem have a geometric interpretation, and one of the earliest paper called post office problems. So um, if we consider the distance as the Euclidean distance, basically this will help us to find the nearest facility. The facility could be post office, could be petrol station, could be shopping center, hospital, and so on and so forth. And in fact, if you use Google Map, by default, if you want to search near me, um, basically they do this kind of L2 version, although um, the the better version should be based on road network distance, but it's much more expensive to compute. So because we have efficient way to perform the L2 version of approximately nearest neighbor or approximate 10 nearest neighbor. This is actually, so the problem is actually well understood in 2 dimension, 3 dimension, or in general low dimensions. But it turns out that it's very hard due to the high dimensionalities. So we won't go deep into it, but whenever the dimensionality is high, many things are first of all, very different from the low dimensional correspondent, and also the complexity usually grows exponentially in the number of dimensions. Okay, so um, for high dimensional um, data points, and if you want to do the exact nearest neighbor query, there are only very few theoretical results which actually can do it in sublinear time. Sublinear means the complexity is strictly smaller than ON, and n being the number of points in the database. So, but in practice, none of these algorithms actually give you good performance. So in practice, I mean, if you insist in exact answers, sometimes just linear scan and do the brute force disk computation and keep the minimum is one of the best things you can do. So if we allow some kind of approximations, we actually can do much better. So actually the version we are going to talk about is actually one of the versions. It doesn't have any guarantee, but it strives to achieve a good balance between the scalability and the accuracy. So in fact, the PQ-based approximate nearest neighbor method is actually one of the most scalable ones. So if you have billions of points, or even tens of billions, that's almost the only way you can do the indexing. So it has a lot of applications. We are going to focus on the machine learning applications. So it's related to so-called representation learning or embeddings. So in spatial clustering, we actually already see one kind of embeddings. So um, one of the this is also related to the so-called dimensionality reduction for machine learning. So whenever you have a high dimensional space, sometimes you want to reduce it to a low dimensional space or a totally different space, such that you can do efficient whatever operations you want. So you start with high dimensional data and run dimensionality reduction and do steps in a small dimensional space. So one of the intuitive example is that this is actually the application built by Eric. I think he was in charge of the technical parts of Spotify, the music recognition engine, and so on and so forth. But I think now she went to another company now. For deep, so basically for even for deep learning, so what you can do is that given a picture. So given a picture, if you really look at each and every pixels, that's going to be very high dimension. Okay, so let's say if this is 200 by 300, and this is color picture, you actually have 3 channels. You have 3 channels. Each channel is actually 1 byte. So you do the multiplication, 200 times 300 times 3. First of all, this is how large each picture is. And in terms of dimensionality, the dimensionality is actually this amount. So you can see that this is pretty large, 10 to the power 5. Right? So what you can do is that you actually finally reduce it to only 1,000, approximately 1,000 dimensions. And this can be done by using state-of-art deep learning methods. Again, this is a very old architecture. Nowadays, we can do things much better. There are all sorts of graph convolution or other kind of networks which can perform this kind of transformation. So once you actually can map each and every picture to a point in the 1244 dimensional space. So what you do is that um, finally you actually they can actually finally uh, use uh, use a bottleneck layer, which actually force everything into 128 dimension. And then what you do is that you actually so you can think about this 128 dimension as some kind of features extracted by the model. Okay, and the network was trained such that it actually try to do the feature extraction very well. So in order to evaluate the distance between any two objects, essentially what we can do is that you can actually use whatever distance, for example, L2 distance. So what they do is that they actually use this is actually the L2 distance, except that um, because the embedding for the two 128 dimensions are not necessarily normalized. So they do the normalization, then do the L2 norm. Okay, so that's the architecture. And then whenever you're given a query image, you can actually go through as long as you can find an object with such that the normalized vector, I mean the because whenever you do the, let's say this is the is this V, this is actually can be done at the query time, and this can be done in the indexing time. So essentially, you are trying to find all the consider all the use in the database, and perform this kind of computation and calculate distance of the query to each and every stored pictures, and you want to return the nearest neighbors or nearest 10 neighbors. So if you really do this, this is your query image, and that's the top 10 results. Okay, so usually we write 10 NNs. So that's the top 10 similar pictures. So as you can see that it's doing a very good job. And in order to do this efficiently, you have to do approximate nearest neighbor search. And in fact, Eric is one of the guys doing this. He actually developed a library called Annoy, which is pretty good. And the reason they need to do that is that they need to do the music recommendation. That's one of the fundamental things in Spotify. So let's look at how the product quantization actually works. Okay, so product quantization works like this. Before we talk about product quantization, we actually talk about the vector quantization. It's called the BQ. Okay, so the general idea is that we want to map each and every real vector, potentially high dimensional real vector, to a low dimensional bit binary vector. Okay, and the binary vector actually records some special meaning, as we will see. So what we do is that, sorry, this should be the d dimension. So whenever you have a d-dimensional vector x, essentially you use some kind of quantizer and quantize. Well, actually, that's why it's called quantization. So quantizer essentially is bunch of d-dimensional vectors, and the x is compared with. You can imagine that you have these other vector. For example, they can be called C1, C2 up to Ck. And whenever you have a new x, you actually are going to use the most sim the code word. By the way, this is called code book, and each one is actually called code word. So you are going to use the code word in the nearest code word to represent this x. Okay, this whole process is called quantization of this vector x, you can think about this as a function. Okay, and once we can do that, then we can actually say that um, the distance between x and O is can be approximate as the distance between x and the quantized version of O. Okay, quantized version will actually become this one of the centers, one of the code word. Okay, code word we also call it centers because essentially we are going to use k-means to do that, and k-means for each of them is a center or centroid. Um, so so as you can see that now x, if we really represent x using C1, uh, we can either record a C1, um, um, I mean, instead of recording x, we just record a C1. But remember that we can actually, the reason we call it codebook is that it's almost like a dictionary or like a lookup table, where if you store all these kind of up to k code words, uh, then you don't really need to directly represent the corresponding code word. You only need to represent its index, right, or its ID. So if you have k code words, you only need log k bits to do the job. Okay, take the seeding if you like. So basically, that's going to be very space say space efficient because essentially the code word are stored only once, and you can refer to it by using the indexes. Okay. So for example, the original dimension is 255 dimension, and if we use 2 to the power of 16 centers, or you use 2 to the power of 16 code words, then we can look at what will be the initial size, and also the size after the, the mapping. So before we do the quantization, uh, for 200 for each vector, for each high-dimensional real vector, got 256 dimensions, and each dimension is 4 bytes. So you are going to use 1k for just one point. Now, if you do something like this, k is 2 to the power of 16, so you only need to use up to 16 bits to encode it. So it's only 2 bytes, right? And of course, you actually have a large code book which you need to store, and this one is actually 250 times 4 and times k, right? So you need to store this one. But this is actually very small. So basically, if there are n data points, it's going to be 2n plus this guy. While here, without using this kind of encoding, it's going to be 1024 times n. Okay, so you can actually see that if n is sufficiently large, even if you need to include the codebook, this one is actually still smaller than the one without using the codebook. But that's one of the advantages. And now how to find the answer? Okay, try to find a point close to Q. So the general idea is that if we run this kind of the way we actually do the quantization is essentially very similar to k-means, in the sense that whenever we determine these kind of centers, let's say these W's, essentially I made the slides. There's a few typos. So let's look at this figure. So these are code words. So these are the code words, and you also have one point here. So they actually uniquely define a partition of the space such that the space was partitioned to cells. Each cell is actually called a Voronoi cell. I think it's spelled like this. So what you have is that within this each of the cells, like this cell, you can actually be sure that this C4, which is this point, is going to be the nearest code word for any of the data, let's say Q or O here. Okay, but if this one moves to here, then the nearest one will actually be C1. So with these kind of properties. So let's say whenever you have a new query, so what you do is that you compute which cell this Q falls into, and for each of the cells, it's easier to essentially what you do is that you calculate distance between Q and each and um, every code word or center, and you determine which cell you belong to, and you can actually find its corresponding code word. Then what you do is that you actually create a candidate set C, which are all the data vectors associated uh, with that particular code word or center. Okay, which is not shown here, but you can actually imagine that in the indexing time, you might have O1, you might have O7, and you might have O5 here, all belonging to this cell. And finally, you do the verification in the sense that you actually load up, let's say O1, O7, and O5, the d-dimensional real vector, calculate distance, and keep the minimum. Okay. Um, So in order to find all the data vectors associated with a particular cell, you actually need a hash table or some kind of inverse index to map each and every code word to a list of objects that are associated with it. So this all looks fine, right? Is there any problem? Okay. One of the problems is that especially this will be more obvious when you have a large number of code words where the space is actually partitioned into finite grids. It's possible that the query belongs to one of the centers, but there is no data points, or there is not enough data points, especially if I want top 10 nearest neighbor. So there might be only one point associated with the current um, cell, and basically that's not enough. You want 10, okay? So basically, we whenever we do the query, we not only need to look into the cell where the query is located, we also need to look at intuitively neighboring cells. Okay, so that's the general idea. But it turns out that for vector quantization, it's not so easy to do. Okay, there are a few ways to do that, but we'll actually focus on one way, which is the PQ, product quantization PQ. So the limitation of this PQ is that in order to achieve better accuracy, fine-grained quantizer with large K is needed. This will help to make sure that the code word and the data points are not too far away from each other. So if they are close to each other, then basically the distance is well approximated. Okay, and in fact, if you want the bound, because it's L2 distance, or most of the distance are actually satisfy the triangular equality, then if you have a code word, let's say this is your x, let's say this is your object, and this is your code word, let's say ck, and this is your query. So this distance and the distance, so the blue one is the real distance between Q and O. Right? Now I'm using the red one to approximate it. So intuitively, if this is small, then basically these two lines are likely to have small difference in the length, in terms of length. So if everybody's distance is approximate accurately, you can answer this kind of queries accurately. But the problem is that and in order for that to be true, you need a large K, large number of large code block. But the problem with the large K is that it's actually very costly to run k-means with very large K. Okay, if you think about in each iteration, you actually need to the amount of work you do is k times n. So basically, if k is very large, this is going to be very expensive. The other thing that computing the cell where the queue is located in is actually very costly as well. So this should be d. That's the dimensionality. Okay. So basically, um, the the cost is that you need to compare with all the k uh, centers or code word, and each one is actually d-dimensional uh, vectors, and the computation takes OD. So basically, it's KD. Um, and as we said, when k is large, there are chances that some of the cells have very small number of points. Um, so you might need to look beyond the current cell. This actually makes things much harder. So there are actually two prominent ways to solve the issue. One is actually to use the product quantization that we're going to talk about. The other one is actually based on the so-called hierarchical k-means. So the general idea is that whenever you have a data set, let's say you partition them into three clusters, and for within each cluster, let's say within each cluster, like then you actually do another level of k-means. Let's say you do you do this kind of k-means. Of course, I mean here you have 1, 2, 3, 4, 5, 6, 7. Okay. Um, then it actually will form this kind of trees. You have three guys, and this one actually give you 7 child. Right. So this is actually the initial k-means, and this is another secondary k-means. So that's actually one way to do that, to impose this kind of hierarchical structure. So product quantization is another idea to solve the problem. So let's look at what it does. Okay, the general idea is that we do not try to deal with the entire. If you think about the hierarchical k-means, you can think about its. For example, if you look at this is our data set. This is our database or data set. The hierarchical k-means kind of whenever you do the first level k-means, let's say these three tuples belong to the first cluster, right? If that's the case, it's almost like a divided counter. So you only need to further divide these three guys into two subsequent clusters and so on and so forth. So they are actually doing the partition on the rows or on the datasets. Now the product quantization essentially do the do the partitioning on the dimensions. So let's say I think this is 10-dimensional vector. So this is 10-dimensional vector, and after doing the partition, typically we end up with two um, we end up with equal length partitions. So basically, that's each subvector. Each subvector will actually become 5-dimensional vector. So as you can see, I'll give you some kind of examples. And then what you do is that for each data set, right? Now you can actually use k-means. Okay, and so after running the k-means, let's say we for each partition, you actually use k-means with k equal to 4. So you use 4 centers. And now in this case, we actually need to refer the center, each center to be Cij, I being the ith partition, and j being the index within that ith partition's code block. So you have C11 up to C14 and the C21 up to C24. Okay, I just list some numbers so you get some idea. And then what you do is for the first, let's say, first subvector in the first partition, you actually look at this code book, you try to find the one which are closest to itself. So let's assume the closest one is actually this one. Okay, yeah, probably it's not this one, but forget about it. So basically, it will actually be encoded as the second uh, code book, which is actually encoded as 0, 1, because in binary everything starts with 0. So this 1 1 is actually 0 0. This is 0 1 1 0 and 1. Okay, and the next tuple will actually be encoded as this guy, and so on and so forth. So then you do the same thing for the second partition. Okay, but again using another codebook. So as you can see, what you have is that um, here it's actually um, if here for each partition you actually use k equal to 4, right? So here you only need to use 2 bits, and if you do the m partition, it's going to be 2m bits. Okay, so if we look at this example, let's be concrete. Originally, each and every vector actually uses 10 dimension times 4, right? So that's the bytes. Now what you have here is that you actually essentially only need to use 2 plus 2 bits. Right. Yeah, sorry. So maybe we just measure everything using bits. Using bits, this is times 8, and here it's actually 4, which is 2 plus 2, right? Of course, I mean, for this solution, you still need to record all the plus code box size, total size. Now you have more than one, right? But in a similar argument, as long as you have large number of points, the second way of doing this kind of encoding is going to be more space efficient. Okay. So once we encode the data using this kind of method, how to perform the query. So before we do the query, we need to look at the distance uh, estimation. So we actually need to calculate in this kind of format, whenever we have a query and we have its encoded basically vector, which is a binary vector, how do we calculate distance? Right. So if you look at this example, they don't even have the same dimensionality. Okay, but as we know that it's not too hard, um, based on the way we construct this kind of mapping, we know that it's actually divided into two partitions, right? It's here. And this one is the index of a particular code. So this one actually, you look up the code book here, and this will actually give you this one. Okay, and so this is the notation wise, it's this one, and for 00, it will actually look up and give you this guy, and you concatenate them together into a row vector, and then for this Q, I think I call it P. You actually can calculate the usual Euclidean distance. Okay, so this is actually done by conceptually, it's like given the encoding t vector and the binary vector t, and the real high dimensional vector q. The Instead of calculating the Euclidean distance, we actually calculate square. Okay, just avoid getting into this kind of square root. So if we do the square on both sides, then the computation is much easier. And also in actual implementation, we really do that because this actually save you to do the square root. Square root is not cheap. Okay, and here what you have is that you actually try to compose into this kind of vector p, and then the q is a d-dimensional vector, real vector, and pi is actually d-dimensional real vector as well. But each part is actually one of the code word in the corresponding code book. And then you do the normal L2 distance calculation. So that's actually conceptually we are able to recover the approximate distance. But in practice, what we do is that if you think about this P is not arbitrary m-dimensional vectors, okay, d-dimensional vectors. It has to be a combination of code word in the corresponding code books. So to be more exact, if we use Q subscript of bracket I to denote the I's partition, the subvector for this Q on I's partition. So basically, this is actually our Q1. This is our Q2. And then for each Q1, I say Q1, it's actually compared with C1. Ti is actually trying to say this is T1. So let's say this is T1. So this is actually the index. You look up the index. We actually, yeah, there are certain notation wise because here we actually, for more readability, we start with 1. But if we start with 0, this equation is correct. Okay, but this essentially says, okay, you look up the code book, and in the first code book or in the I's code book, because we're looking at the I's, you actually use the corresponding segment in T to do the decoding to find the corresponding center. Then you actually calculate the Euclidean distance, and you sum over all the partitions. Okay, you probably want to think about why we can do something like this. The key part is that the Euclidean distance is actually we actually say this is a distributed. We can do distributed computation because essentially you can accumulate partial Euclidean distances and then sum them together to get the final one. Okay, so if you like, this is your P, and then yeah, we can do the L2 distance, right? And if you look carefully, this is actually this part, and this is for the second partition. Now, finally, we look at how to perform query processing. Okay, so for query processing, what we can do is that we can have a naive version. So the naive version that we perform this kind of. Oh, by the way, this is actually called asymmetric distance. Okay, in the paper they call it asymmetric distance computation, but really it's asymmetric distance. There is a version called symmetric distance, but again, asymmetric one is better and no more expensive to compute. So we only focus on asymmetric ones. So how to do query processing? So it's kind of similar to the vector quantization if you don't have any good ways to do that. So the general idea is that the distance is actually, instead of having a physical center, and you can actually use the distance between query point and the physical center as instead of the distance to the object. Now you actually, for every object, so for every T in your database, right, you actually calculate its corresponding ADC once a query is given, and then you actually can grab the smallest k of them, and even if you only want to return one of them, sometimes you can perform something called a re-ranking, in the sense that you actually fetch more than what you require, and you can load the data vector to compute the actual Euclidean distance. because remember, the one we actually calculate is not the real Euclidean distance, but it's actually one of the approximations. So if you really want, you can actually do this kind of ranking by really loading the vector and trying to figure out what exactly is the distance, and then return the one with the smallest distance. Of course, this is optional because this is expensive. It requires loading, high-dimensional vectors. So in many cases, um, basically we can just return the the k. If you only require one, you actually return one with the smallest AD. Or you can do ranking based on some other criteria. Okay, so that's the general idea. So if we do something like this, the cost is actually ON, right? Although the constant hidden inside could be smaller because the dimension is smaller. Okay, can we do better? So one of the things we actually can do is that because you know um, the, the 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 p if you like, is not any arbitrary. It's not any arbitrary value. So and it's decomposable, as we can see that the distance between q and p is actually the distance between. You can imagine that it's actually the distance between the first part and this part, right? And together with the distance between these two parts, and put them together. I'm talking about a squared Euclidean distance. Okay, otherwise you put them together, sum them together, and take the square root. So, um, so that's just the equation again, and let's think about any two, um, you know, binary vectors encoded by product quantization. Now we know that for this vector, right, for these two guys, essentially for the first partition, they load up different uh, code book or code word in the code book to do the calculation, and they actually only look at this one, right? So as you can see, if you look at the formula, this is the AD for T, this is the AD for T prime, right? So the, the observation is that this is a fixed, right? So this is the only variable, okay? And if the code book have 4 code word, essentially you can actually see that the number of choices are only 4, right? And among the 4s, if you really do the calculation for each and every CI1 up to CI4, you can actually calculate you can actually know, you can actually sort all the code books according to this distance, with respect to q. So in other words, if you again, it's a high dimensional space, but it looks like, for example, this is our q, and you have let's say C1, C2, and the C3, and let's say C4. Then essentially, um, the order, the increasing order based on the partial, I call this partial AD, is that the order should be most likely C4, C1, C2, and the C3. Right? So that's the most likely order. So, and you do the same thing for the second partition, right? Now, if I tell you that this one is actually smaller than this one, okay, and this one is smaller than this one, right? Okay, if I tell you that this information, we actually know that basically the AD of the AD of t is actually smaller than AD of t prime. Right? Of course, I mean you can argue that if this becomes greater or equal to, then we cannot have a deterministic answer. but at least we know that okay, this is true. Okay, and if we given a q, we know that if this is the so this is actually q between the distance between q and so this is essentially the distance between q and the CIT1, right? For example, if we forget about the double indexing, it's easier. So this one is actually smaller or equal to, or in our example, is smaller than q uh, 2. So this is actually q minus c1 and smaller than all the other code blocks. So if it's smaller, if you take to this raise it to power of 2, the inequality still holds. Right? So basically, you know that there is an optimal order to consider each encoded points because they are going to have different ADs, and we can actually um, finally, I mean, if you really compute all the ADs, definitely there is an order. But it turns out that if we can identify earlier, um, you know, what are the next smallest, uh, next possible um, tuple or data points with the smallest AD, then the efficiency of our algorithm will actually improve. Now the hard part is really to do this efficiently and incrementally. Okay, incrementally you don't really want to, you know, even if there is an optimal sequence, you don't want to compute it, you know, exactly. I mean, in its entirety, because um, most likely you only need the beginning part of it. But the question that you don't know how many entries you need before you actually find a real satisfactory answer. Right? So you want to calculate this incrementally in the sense that give me the next smallest, you know, give me the next tuple with the smallest AT. Right? So the algorithm looks like this. Okay, and the algorithm is very similar. It's not the same, but usually I use this kind of Minesweeper. It's game in all the Windows. The good thing that it have this kind of grid system. Okay, and um, the whole idea is that uh, the so-called multi-indexing algorithm actually have two steps. The first step is to sort each codebook in increasing order of their partial AD distance to Q. Actually, AD is already distance, AD to Q. So basically, we use the example in the paper in the sense that um, whenever you have Q1 and they use the first partition, again it's two partition. The first partition, the codebook is denoted as this big U, where each vector is denoted as U1 up to U6. Okay, and it turns out that U3 is the closest to this vector. So Q subscript of brackets 1 is a subvector, and R and this S are its partial asymmetric distance. Okay, as you can see that it's actually in increasing order. So U3 is closest to Q subscript 1, and U4 is the next closest one, where U6 is pretty far away. Then what you do is that again we just use the order in the sorted sequence to denote all the code words, and just consider this guy. Just consider this guy. Okay, this guy have the coordinates I and j. So let's say in this case I equal to 3, j also equal to 3. Right? So that's going to be u5 and v5. If you really want to figure out the high dimensional vector, you actually put u5 and v5 together. That's not necessary. Right? So we know that this is actually the darkest red cell. And if you consider the one next to it, okay, the one next to it, let's say this one, right? Um, its coordinate will be I plus 1 and j. Okay, so and also if you look at the further down it's going to be I plus 1 and j plus 1. Okay, so we actually say that the AD of this red cell dominates the AD of this you know sort of like light red light red cell, and it's actually dominating the AD of you know the, the, the yellow cell. So AD, so basically this AD is smaller or equal to, and smaller or equal to. So that's the dominance relationship. Okay, it's easy to see what's why, right? So uh, simply you can actually use the example to verify. So basically for this ducks, because of the example here, for this guy, the partial distance is actually 4 plus 3 equal to 7. Right? And for this guy, let's say talk about I plus 1 and j. I plus 1 is u2 and j. So that's going to be 3 plus 6 is 9. And for this one, it's going to be 6 plus 6 equal to 12. This is pretty straightforward. So the general question that this dominance is not only between the adjacent cells or computations. For example, this one also dominates this one. Okay, you can easily see it. So the dominance is really like to the bottom right. So this guy actually dominates everything here. Okay, but there are actually cases where, for example, if you consider this guy and this guy, okay, they don't really have any dominance relationship because this guy actually dominates everything here. This guy dominates here, but you can't say anything like which one is larger, hence which one dominates which one. So we only need to pay attention to the adjacent ones because essentially this enables us to do things incrementally. So just to recap, whenever you are considering the ij, right, you push your two neighbors. That's your two neighbors because in 2 dimension. Okay, in 3 dimension you have 3 neighbors. You actually push all the neighbors into a special data structure called min heap with their and so basically whenever you push this entry, the key will actually be the corresponding score. Okay, just like this one. So you push this red cell into the heap with the key equal to 7, and the min heap actually will allow you to extract the entry with the minimal key value in efficiently using log let's say log t operation cost, and where t is the size of the heap. Okay. So one of the subtle issue that if you really think about it, then each of the cells, let's say this guy will actually be pushed in by this neighbor and this neighbor, right? So this guy will push its right neighbor, and this guy will push its next, next row neighbor into the heap. So you definitely don't want the same thing to be pushed twice. So you should check whether it has ever been pushed into H or not. So typically you can use a bitmap or some kind of data structure as a data structure to maintain this kind of information. But there are actually clever ways to do that. So let's look at this example in running. So basically what you do is always start with 1, 1. Okay, that's the best computation you can ever get. So the distance will actually, the AD will actually be 0.6, which is 0.5 plus 0.0. So once you process this guy, before you remove this guy from further consideration, remove this guy from the heap, what you do is that you push its neighbors. Okay, its neighbor is actually 1, 2, which is this one. This is the I, this is the J. So basically that's going to be 2, 1 and 1, 2. So you push 2, 1 and 1, 2 into the queue. Right. So all the white guys are actually, we list all the value there, but it doesn't really matter. Okay, we as far as the algorithm is concerned, all the white cells actually are unknown. It's like have a have a fork there. Then after you process, I mean, what after you process this guy, um, you remove it, right? You remove it, and in the so the current heap actually contain only 0.8 and 2.5. So what you do is that you actually take the minimal, extract the minimal entry from the heap, which will be 0.8, and then what you do is that you actually push the neighbors of, I mean, immediate dominant neighbors into the heap. So you push 4.1 and 2.7. Okay, so that's why they are this kind of shape. And once you process this cell with a partial distance 0.8, so by processing it means okay, load the data points corresponding to this cell. Then you actually mark this one as already done, and in the rest of the cells you actually take the minimal, which is 2.5. So for 2.5, you actually push its two neighbors, 2.7 and 3.5 inside, but it turns out that this 2.7 does not need to be pushed again because 2.7 currently is already in the heap. Right? It could, it could be the case that 2.7 is already processed, so hence a black one. But anyway, you have already considered this entry, so you don't want to push this entry again into the heap again. And this algorithm goes on, and you can actually see the final results. By the way, the algorithm is actually called skyline. So why it's called skyline is that if you look at the trajectory, it's always going to be like this. Okay, like this kind of zigzag. This is kind of like the skyline where if you let's say if you see from distance, okay, the further away buildings, you can only see them if they are higher. Okay, so they will actually form this kind of skylines. And so so if you think you are clear, you can actually write out the edge at each step and think about how to perform the dedupe. Actually, the paper actually give you the details, and you really need to think about. Okay, so these two questions are going to be harder and harder. So this one actually means, can you generalize this into more than 2 dimensions? Okay, all the example in 2 dimension. In multi-dimension, it's hard to visualize, but you need to feel comfortable that okay, you know that the algorithm can be generalized into let's say 3 dimensional or even 10 dimensional space. 10 dimension means okay, you partition the vector into 10 sub vectors, right? And the harder part is that you can perform this kind of deduplication without using additional data structure and cost. Okay, so the paper actually need to maintain sort of like a bitmap or hash table to do that, but essentially you don't really need that. Okay, so this is actually the two paper we actually are going to use, and for more details you can actually look at the project specification where there will be more details on what exactly you need to do in the project. Okay, so let's have 10 minutes break, then we'll move on to the next part.